Hello everyone, my name is Jialu. Today I'm going to present our paper, Improving Vision Language Navigation by Generating Future View Image Semantics. My collaborator is Mohit. In vision language navigation, the agent takes the next action by selecting from a set of navigable locations. This action selection process does not take advantage of humans' ability to expect what thing will be more likely to happen next during navigation. Thus, we explore whether AI agents could benefit from the ability to generate future scenes for action selection. To achieve this, we propose 3 proxy tasks for VLN pre-training, which predicts missing steps in the full trajectory, predicts missing views in a panorama, and generates the next view. We further propose codebook selection and overall semantic computation to compute the target semantics. We then fine-tune the agent on the VLN task with APIG as an auxiliary loss to inject visual semantics. Empirically, our approach achieves the new state-of-the-art on both room-to-room dataset and CVDN dataset. After briefly introducing what we've done in this paper, we will introduce the task, our method, and the results in more details now. To first compute the overall image semantics, we tokenize the view images into visual tokens with a pre-trained discrete variational autoencoder DVAE. While the pre-trained DVAE has a large vocabulary of 8,192, we propose dynamic codebook selection process to optimize a subset of codebook at one time during training. This helps the agent to learn the more important tokens and focus on optimizing more difficult tokens. Specifically, the importance score is based on how frequently visual tokens appeared in the images. The difficulty score is based on the difference between the agent's predicted probability and the ground truth probability. Then we propose and compare 3 ways based on mean value, block-wise weighted value, and sampling to represent the semantics of all patches for efficient image semantics learning. Specifically, mean patch probability uses the mean of all the patches probability to represent the image. Sample patch probability uses the semantics in the sampled patch to represent the image. Block-wise weighted patch probability uses the weighted average of all patches to represent the image. The block-wise weights helps the agent learn the richer semantics in the blocks in the images. To equip the agent with the ability to generate the semantics of future navigation views, we pre-train the agent on 3 proxy tasks. In mask trajectory modeling, the agent learns to predict the semantics of multiple steps in the full trajectory. In mask panorama modeling, the agent learns to predict the semantics of multiple missing views in a full panorama. Mask panorama modeling and mask trajectory modeling together give the agent the ability to understand the semantics in each visual token and learn to recognize the semantics contained in each view. In action prediction with image generation, the agent mimics the navigation process to predict the next step by generating the visual tokens contained in the next navigation view. This task enables the agent to imagine the next step view semantics before making actions. We then fine-tune the agent on the step-by-step vision language navigation task. We further enhance the agent's ability to predict future views by optimizing an auxiliary task during navigation, which minimizes the difference between the predicted observations and the target observations. We conduct experiments on 2 datasets, room-to-room dataset and CVDN dataset. The evaluation metrics we use include success rate weighted by pass length, normalized dynamic time wrapping, success rate weighted by normalized dynamic time wrapping, and coverage weighted by pass length. Among all these metrics, success rate measures the agent's ability to reach the target. Normalized dynamic time wrapping and coverage weighted by pass length measures the agent's ability to follow in the instruction and not deviating from the path. Our proposed approach achieves the new state-of-the-art on both room-to-room dataset and CVDN dataset, outperforming previous DOTA agents by a relative gain of 4.5% in goal progress on the CVDN test leaderboard and a 3% absolute gain in success rate on the room-to-room test leaderboard. We then demonstrate the effectiveness of our proposed 3 proxy tasks for VLN in domain pre-training. We show that adding any of our proposed tasks improves the performance by a large margin in both success rate and SPL. Then we demonstrate that it's important to select a subset of visual tokens, either statically or dynamically, for the agent to effectively learn the large visual token vocabulary extracted with pre-trained DVAE. We further show that our block-wise weighted function helps the agent to learn the image semantics better, improving the baseline by more than 3% in both success rate and SPL. Lastly, we show that our model could reasonably generate future semantics and reconstruct future images. We generate the token for each patch in the image with our APIG head learned with weighted patch probability. We set the weight to be an indicator vector to generate the semantic. We use 70%, 80%, and 90% of the patches with ground truth tokens encoded with pre-trained DVAE. The rest patches with the tokens generated by our APIG head. And then we use a DVAE decoder to decode the image. Our generated image could almost reconstruct the beds and pictures in the original image with small vague areas when given 70% of the ground truth tokens. In comparison, filling 30% patches with random tokens will generate distorted images with large white parts, and the beds and pictures information cannot be identified. We also notice that our model still fails to generate the full image when all the tokens in the image are predicted by our APIG head, and needs at least 70% of the ground truth tokens to generate the images of reasonable quality. Our code is publicly available at the following link. Thanks for your attention.